We're going to start Unit 4 by exploring what polynomials do graphically and kind of understanding some of the basics. First thing we have to do is make sure we remember the zero product property. We spent a lot of time last unit talking about it, but basically that means that if we have numbers that multiply together to equal 0, then one of those numbers has to equal 0. That also applies if we have more than one or more than two things multiplied by each other. So if I have A times B times C equal to 0, that means that A is 0 or B is 0 or C is 0. And then that is a way that we can conclude that if we have something like x minus 2 times 2x plus 3 times x minus 5 equal to 0, then x either has to be 2 in order to make x minus 2 equal to 0. X has to equal negative 3 halves in order to make 2x plus 3 equal to 0. Or it has to be 5 to make x minus 5 equal to 0, because one of these three numbers, so to speak, has to be 0 in order for this multiplication to end up equaling 0. And so what does that mean for us graphically here? Well, if we take a look at this problem, I see that negative x times x minus 1 times x plus 2 times x minus 2 times x plus 4 equals 0. And so what that means for us is that by the zero product property, either, I can kind of ignore this negative sign out front because that's not going to really have any effect on when things are 0. But if I take a look at 0 equals negative x times x minus 1 times x plus 2 times x minus 2 times x plus 4, what that means is that either x has to equal 0, x minus 1 has to equal 0, which means x equals 1, x plus 2 has to equal 0, which means x equals negative 2, or likewise, x minus 2 or x plus 4 equaling 0 means x equals 2 or x equals negative 4. All of these things, any one of these things must be true in order for this function f of x to equal 0. And so if that's the case, that means that I know all 5 of my roots. I have 5 roots in this problem. I have a root at x equals 0. I have a root at x equals 1. I have a root at x equals negative 2. I have a root at x equals 2. And I have a root at x equals 4. So I can put all of those things on my graph. So I know I have 0, 0, 1, 0, negative 2, 0, 2, 0, and 4, 0. All of those points intersect my graph. I can also figure out my y-intercept pretty quickly because I can find where x equals 0. And so if I substitute 0 into my function, I will end up getting 0. In this case, that's pretty simple because I already knew that that was a value on my function when I substituted in 0. But even if I just did that right away, f of 0, I would get 0 pretty quickly. And then 0 times everything is 0. So we kind of have a general idea anyway as to what this graph is going to look like in terms of where the intercepts are. But now we kind of have to figure out what it's going to look like otherwise. So let's take a look at what happens as x approaches negative infinity. So obviously x can't actually equal negative infinity, but what happens as the x values move further and further to the left? So if the x values move further and further to the left, let's take a look at what happens in the function. So if I take a look at f of x, if I plug in some negative giant number. So if I plug in some negative giant number into f of x, I have negative times some negative giant number times some negative giant number times a negative giant number times a negative giant number times a negative giant number. So notice I have a negative sign and then 5 more negative giant numbers. If I multiply all those things together, I'm going to end up with 6 negatives all multiplied together, which ends up equaling a positive giant number. So as I look at the graph, as x goes to the left forever, my function is going to get positive, bigger in the y direction. So that is how my graph is going to go forever and ever and ever as x goes to the left. Now, if I try to do the same thing when I substitute in a giant positive number for x, I have a negative sign, and then all of the other numbers are going to be positive giant numbers in my original function. So if I look at this, positive, 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 when I substitute in a giant value of x in the positive direction, I just have one negative. And therefore, this is going to be a negative giant value of y. So as my function goes to the right forever, my value of y is going to go down. And so my graph is going to look something like this. And what's going to end up happening is I intersect the x-axis at all of these points. And my graph will somewhat look like that. We'll take a look on the calculator to see why some of those go way lower and some of them go way higher than I'm actually drawing. But to the best of my knowledge without a calculator, that's something that I would be able to draw. So as x approaches negative infinity, the function approaches positive infinity, and as x approaches positive infinity, the y values or the function approaches negative infinity. If I look at this first graph on the Desmos graphing calculator, what you'll notice is that this value goes way low, and this value goes way higher than I would actually be able to graph it by myself, just without a calculator. But if I kind of zoom in a little bit, I can see what's happening. So I have these values that would be like locally where things go lower than anything kind of in its general area. But if I'm looking, I see that the graph doesn't actually have any maximum or minimum, because if you look at the end behavior, since the end behavior goes in opposite directions, the maximum y value would be positive infinity, and the minimum y value would be negative infinity. My maximum will be there is no maximum, and my minimum will also be that there is no minimum. Quickly, let's review some things about the TI. If I graph this first equation on the TI, I'm going to have to change my window in order to see anything. So I would probably, it appears that the x values are good, but I would have to change my y values quite a bit in order to be able to see everything effectively on the graph, like where the low and high points would be. So if I look at this, I realize that my roots are at 2, -3, and 4. So 2, 0, -3, 0, and 4, 0 are my roots. So I know that. My y-intercept, if I substitute in 0 for x, I get f of 0 equals 1/24 times -2 squared times 3 times -4. So I can do a little bit of mathematics. 4 times -4 is -16, times 3 is -48, and then I divide that by 24, so I get -2. So I have 0, -2 as a value. I'll figure out the max and min later. But let's take a look at the end behavior. The end behavior, if I sub in very negative giant values of x, if I want to take a look at negative giant values of x, so f of a negative big number, that's going to be 1/24th. And then this is going to be negative squared. This is going to be negative, and this is going to be negative. So that's 1/24th times positive times negative times negative. That ends up being a positive number. So that goes off to positive infinity. Sorry, it's not supposed to dance like that. So this ends up being positive big when I substitute that value in. If I'm trying to find what happens as I plug in a big number, positive big, I end up with 1/24th times positive squared times positive times positive. Obviously, that's positive as well. So my graph ends up looking like that as x's get more and more to the right. So as x goes to the left or to the right, it doesn't really matter. My function is going up forever. And so it appears that I cross here. I should somehow hit this point. I cross here. Oh, wait a minute. I have an issue. I can't cross again because it's supposed to go up forever. So I need to analyze this situation a little bit more before I do this. Notice I have an x minus 2 squared. Well, remember last chapter, if I had y equals x minus 2 squared, that meant that this was a double root of some kind of quadratic. And on a double root, it hit the axis and bounced back up at 2, 0. Likewise, this is going to be a double root as well. So at the point x equals 2, this is going to bounce. So it's going to cross at every other point. So it's going to cross. Then at this point, it's going to bounce. And then it will cross the axis again at 4. And so this is a rough sketch of what my graph is going to look like. Now, if I take a look at the Desmos version of this, my graph is there. That's a little bit better. So I can figure out my minimum value is at negative 1.628, negative 4.235. And then I want to find a max, but I don't have a maximum value. So my minimum value is at negative 1.628, negative 4.235, but I don't have a maximum value because it goes up in both directions forever. If I graph the second function on the TI, I would have to redo where my window is again. In this case, the window would actually be pretty good to do a zoom standard to go back to negative 10 to 10. I'll be able to see everything. And if you notice, there is a minimum on this graph, which we found in the Desmos graph. So if I do second trace, I can do a minimum or a maximum. In this case, I want a minimum. And remember, I have to bound it to the left and to the right of my minimum and make sure that I have the minimum included in this boundary. And as you can see, it finds the minimum negative 1.628, negative 4.325. We're going to quickly do these two problems. I will factor them for you and then get everything into what we need in order to graph the polynomial. So I have f of x equals x times x squared minus 8x plus 15 with the greatest common factor. And then when I factor the last part, I get x times x minus 5 times x minus 3. So that means that I know my roots are at 0, 0, 5, 0, and 3, 0. So if I put those on the graph, it will look like that. My y-intercept is at 0, 0, which I get just because I already knew that. And then if I'm looking at my end behavior, if I substitute in a negative big value and a positive big value, what will end up happening when I plug in the negative big value is I get negative times negative times negative. So I get a negative big value. And if I plug in positive, I get positive times positive times positive. That ends up being a positive big value. So my end behavior, as x approaches negative infinity, the function approaches negative infinity. And as x approaches infinity, the function approaches infinity. So my graph will look something like this. And I don't have any double roots over here. So because I have no double roots, the graph will look something like this. And since the graph looks something like this, where they're going in opposite directions, I don't have a maximum or a minimum value of this function. So that would be what that looks like. Final problem. This one, I would probably want to factor out the negative sign first. And then I can factor this again into x squared minus 9, x squared minus 4, which is something we learned last chapter. So f of x equals negative x minus 3, x plus 3, x minus 2, x plus 2. And if I look at the roots, I have roots at 3, 0, negative 3, 0, 2, 0, and negative 2, 0. So all of those things will end up giving me roots. I will plot the roots on the screen. The y-intercept is negative 36, which is obvious because that is the value that when I plug in 0, I get negative 36. So we'll just make this value negative 36, since that would be way off my graph otherwise. And then if I look at the function, if I plug in negative big values of x, I get negative, 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 negative. That ends up being 5 negatives. So that's a negative value. If I plug in positive big values of x, I get negative, positive, 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 and that's 1 negative. So that, again, ends up being a negative value. So my end behavior looks something like this. Negative infinity both sides. So it'll look something like that on my graph. I'm not going to have a minimum value because it goes off to negative infinity. The y values do in both x directions, but I will have a maximum for this graph. So if I want to look at that on my graphing calculator or Desmos, I'll do it on the graphing calculator. I end up with two different values. They end up being the exact same y value. So negative or positive 2.550, and then 6.25, which I actually don't have to round because that is a fraction that has a terminating decimal there. I did the favor of multiplying out the first two polynomials for us. So the problem 1 is negative x to the 5th minus 3x to the 4th plus 8x cubed plus 12x squared minus 16x. That's what happens if you do all the distributing. And likewise for problem 2, I put that down here. So what I want to do is just graph these real quick and kind of look at what's going on the 4 problems that we have. So what I notice about the first and the third problem is they had an odd exponent. And notice that with the odd exponent, the direction of the end behavior is opposites. So in the first problem, it goes as x approaches negative infinity and x approaches infinity, the y values go in opposite directions. Likewise in the third problem. Whereas in the second and fourth problem, notice that the y values go in the same direction. And that makes sense. I'm going to put all of the odd powers here. Notice that they're going in opposite directions as x approaches negative infinity or x approaches infinity. But if I get a negative leading coefficient, they still both go in opposite directions. So this is something that is true about all odd powered, like when the biggest degree is odd. Now, if the biggest degree is even, they're both going in the same direction. So as x approaches negative infinity or infinity, the y values both go in the same direction. And that's true whether our leading coefficient is positive or negative. Another thing we might want to notice is that the most amount of turns that I have on a function is going to, so this purple graph has 3 turns. Notice that the leading or the power is 4. Um, Likewise, on the red one, the power was 4. And I can see that there are 3 turns on the red graph as well. When the power was 3, notice I only had 2 turns on my graph, maximum anyway, maximum amount of turns. And then with this graph, the x to the 5th, I need to change my window a little bit just to see it better. But I can see that I have 4 turns on this graph. And notice that the maximum amount of zeros on a graph is the same number as the leading power. So these are all things that we can kind of summarize here. The shape of the polynomial, if the degree is even, then they go in the same direction, the end behavior. If it's a positive leading coefficient, they both go up. Negative leading coefficient, they both go down. If it's an odd degreed polynomial, the end behavior goes in opposite directions, as shown on the screen. The maximum number of turns is 1 less than the degree, and the maximum number of roots or maximum number of x-intercepts is equal to the degree. Notice I put the word maximum because it's possible that I could have fewer of those in certain circumstances, but these are the maximum amount. And then notice that a root crosses the axis if it's to the first power and bounces if it's to the second power. And then we'll learn about other situations later. But that's something that we noticed when we saw in problem 2, we had this double root.